Artificial general intelligence, AGI, it's one of those concepts that really grabs your attention, doesn't it? We see it everywhere. Movies, news.
Definitely. But beyond the, let's say, Skynet hype, there's actual serious research going on.
Right. Though, as the paper we're looking at today points out, even the experts are still, well, debating what AGI actually means. It's not straightforward.
That's a key point. The popular image is, yeah, dramatic. But to really get it, we need to look at the foundational ideas driving the research itself.
Exactly. So for this deep dive, we've got this recent paper. The aim is kind of a short, accessible, but also, thought-provoking overview, trying to cut through the noise.
Moving past the sci-fi.
Yeah, moving past the sci-fi, getting into the core concepts that scientists are actually wrestling with. And the paper kicks off right there, actually, looking at how different people even define this thing.
Which is, well, crucial, isn't it? Because if you don't agree on the target, well, there just isn't one single definition everyone signs up for. The paper lays out a few key ones.
Okay, let's unpack some of those then. There's one definition that feels pretty intuitive, AGI, as like reaching human-level performance across a whole bunch of tasks.
Sounds simple enough on the surface.
It does, but the paper makes a good point. Isn't that a bit too focused on us, on what humans can do? And how do you even measure human level across everything? Seems tricky.
Precisely. It's very anthropocentric. That's the term they use. Then you've got Chollet's take, which shifts the focus a bit.
Okay, how so?
He talks more about the ability to learn and adapt, saying AGI is about being able to generalize, pick up new skills, at least as effectively as a human does. The key there is adaptability.
Adapting to new stuff.
Yeah.
That makes sense. And that connects to another idea, right, from Legg-Hutter.
That's right. They define intelligence as achieving goals across a really wide range of different environments.
And the paper links this to simplicity, like Occam's razor.
Yeah, and also to something called Kolmogorov complexity, which is basically about how concisely you can describe something. The simpler the description, the better, in a way.
Interesting. But the paper also brings up this underlying assumption, this potential issue with how we often think about intelligence itself.
Yes, exactly. This idea of computational dualism. It's like separating the software, the mind, from the hardware and the environment, the body, and the world it's in. Wang's work highlights this.
Right, like studying bird flight just by looking at wing code without the bird's body or the air. You miss the whole picture.
You do. So Wang defines intelligence more like adaptation with limited resources. It brings the whole system, software, hardware, environment, constraints into focus.
Which is a big shift, isn't it? Less about raw power, more about efficiency, how well it learns and operates within limits. That seems really important for, well, real-world stuff.
Absolutely. And building on that, the paper suggests a working definition for this discussion. Think of an AGI system as one that can adapt, at least as generally as a human scientist.
A human scientist. How so?
Well, someone who can figure out what's important, design and run useful experiments, learn cause and effect, and, balance exploring new things with exploiting what they already know.
Okay, I like that framing, the artificial scientist. And the paper also makes this point about how we usually categorize AI, supervised learning, reinforcement learning, all that.
Yeah.
It says those might not be the best buckets for thinking about AGI.
Because that artificial scientist needs the whole toolbox, right? It can't just be one thing. So instead of those categories, the paper leans on Sutton's bitter lesson.
Ah, the bitter lesson. Remind us.
It basically says that, in the long run, the methods that win are the general ones that scale well with computation. Methods that can learn almost anything given enough data and processing power, rather than relying on, say, specific human-coded knowledge.
Got it. So focus on the general tools, which brings us to the core of the paper, right? These are foundational tools for building adaptive systems. The first one is search.
Right, search.
Now, when I hear search, I think Google. But that's not quite what the paper means, is it?
Not exactly, though there's a connection. Informally, the paper defines search as, like, taking a structure that already exists and finding a solution within it.
Okay.
Like planning a route on a map app. The map is the structure, roads, junctions, and the app searches through possible paths to find the best one.
Ah, okay. Like solving a maze. And formally, they talk about algorithms like A.
Exactly. Algorithms like A are used for planning, symbolic reasoning. You have rules, and you systematically explore actions to reach a goal.
And this has its strengths, obviously.
Oh, definitely. Search can give you answers that are provably correct, according to the rules you set, and you can usually follow the steps. It's interpretable, great for planning, theorem proving.
And the paper mentions the chess example, Deep Blue.
Yeah, Deep Blue beating Kasparov back in the 90s. That was fundamentally a very, very sophisticated search through possible chess moves, learning by exploring hypotheses, basically.
That's a great example. Right. But search isn't the whole story, is it? The paper points out some downsides.
Absolutely. For problems with massive state spaces, think navigating a city block by block with infinite path choices, search just becomes computationally explosive, really expensive.
You could try to add constraints, rules to narrow it down.
You can, but then you limit its adaptability, its generality. Plus, traditional search is often sequential, step by step. It doesn't naturally leverage modern parallel computing hardware as well as other methods.
So it works best at a higher level, with symbols and clear rules.
Pretty much. Effective when you have a good symbolic representation of the problem.
Okay, so that's search. What's the other big tool the paper discusses?
Yeah.
Approximation, or what Sutton called learning.
Right. They use approximation because, as the paper notes, even search can involve learning. But approximation here is more about starting with a model and tuning its parameters based on data.
Like training a neural network for image recognition or text generation.
Exactly that. You feed it data, and it adjusts itself to approximate the patterns in that data. Image classification with CNNs, text generation with transformers, those are prime examples.
So instead of explicit rules, it learns the patterns itself. And the advantages there are.
Well, it's really good with noisy, complex, real-world data where search might just get lost. And crucially, it parallelizes really well on modern GPUs and TPUs. That's a huge reason for the recent boom.
But the name itself, approximation, hints at a weakness, right?
It does. It's inherently inexact. That's the trade-off, which can lead to unexpected errors, and it's often a black box. Hard to know why it made a certain decision.
And for AGI specifically.
The current methods tend to be very sample inefficient. They need tons of data and energy hungry, and they can struggle with novelty with edge cases they weren't explicitly trained on.
Right. So, okay, pure search has limits. Pure approximation has limits. Neither seems like the complete AGI picture on its own.
Exactly. Which leads naturally to the next section in the paper, hybrids and more complex architectures.
Combining the two. Makes sense biologically, too, probably, using different strategies.
Absolutely. The paper really emphasizes their complementary strengths. Search for structure, approximation for handling fuzziness and scale, and combining them can lead to much more powerful, flexible systems. AlphaGo is the classic example here.
Ah, yes, the Go champion. How did that work again in terms of this hybrid idea?
Well, it used Search Monte Carlo tree search to explore the massive tree of possible Go moves. But crucially, it used deep neural networks, an approximation technique, to evaluate board positions and predict promising moves.
So the search explored possibilities, and the neural net provided the sort of intuition.
Exactly. The approximation guided the search, making it feasible to tackle Go's complexity, a brilliant synergy. But, the paper notes, the search part still operates on human-defined symbols the game moves, which raises the symbol grounding problem.
How do these abstract symbols connect to the messy real world?
Right, and that's where things like neurosymbolic hybrids come in.
Using neural nets to interpret raw input, like images or sensor data, into symbols.
Precisely. Turning perception into a symbolic form that a search or reasoning engine can then work with for planning or inference. And the paper stresses how you choose to represent the problem symbolically is critical.
Getting the right symbols makes all the difference.
Huge difference. The paper also mentions structured reinforcement learning using approximation, maybe autoencoders, to compress high-dimensional sensory data into a more manageable symbolic state space for better adaptation.
Okay, and there are newer examples too. The paper mentioned OpenAI's O3.
Yes, O3 blends approximation with a more structured chain of thought style reasoning for complex problem solving.
And DeepMind's alpha geometry.
Another great example. Using neural nets for pattern recognition in geometry diagrams, combined with a symbolic engine to actually deduce the proofs. It shows the trend towards integration.
So beyond specific hybrids, the paper talks about broader frameworks. Cognitive architectures, autonomous machines. Sounds like building a whole mind.
Kind of, yeah. Modular systems with components for perception, memory, reasoning, maybe like System 1 and System 2 thinking.
Like giving neural nets a scaffold for memory and identity.
Exactly. Providing structure. Early attempts include systems like SR and ACTR, which have been around for a while.
But there are more recent ambitious ones. Hyperon, Arrie, NARS.
Right, these are aiming for something more integrated and, well, general. Hyperon is described as modular, distributed, combining probabilistic logic, neural nets, a knowledge metagraph, aiming for holistic cognition.
Designed to be scalable and self-organizing.
Yes, and potentially integrate new ideas like active inference down the line. Then there's AAU, the autocatalytic endogenous reflective architecture.
That name sounds complex. Autocatalytic. Reflective.
It implies self-improvement, self-programming, essentially. AFE-Lee reflects on its own symbolic structures while learning statistically from data. Focuses on analogy, causality, autonomy, growth, predictive modeling. Very proactive adaptation.
Wow. And NARS, non-axiomatic reasoning system.
NARS operates under a key assumption, insufficient knowledge and resources, or AIKR. It uses a fluid, adaptive logic, non-axiomatic logic, NAL, not rigid axioms.
So it's designed for uncertainty. Incomplete data.
Exactly. It integrates symbolic reasoning with probabilistic inference, learning incrementally in real time.
So these hybrids and architectures, they seem to offer a lot. Efficiency, interpretability, maybe better ways to use human knowledge, and autonomy.
Those are the big potential advantages, yes, especially enabling more genuine autonomy. But the paper adds a note of caution.
Challenges?
Yeah. Harmonizing these very different methods, symbolic logic and fuzzy neural nets, for instance, is technically difficult. And there's a risk of just building ad hoc systems without strong theoretical grounding.
Makes sense. Which I guess leads us to the final piece the paper discusses. These meta approaches, high-level philosophies.
Exactly. We have the tools, search, approximation, we have ways to combine them, hybrids, architectures. Now, what are the guiding principles for building systems that are genuinely adaptive? That's what meta approaches are about.
Like general rules, choose the simplest solution or something.
Sort of, yeah. Principles for optimizing adaptability. The paper groups them into three main types based on what they try to maximize.
Okay, what are they?
First, there's scale maxing, which connects directly to Sutton's bitter lesson.
You just make everything bigger. More compute, more data, bigger models.
Pretty much. That's dominated recent history, hasn't it?
Yeah.
The paper calls it the embiggening. Huge language models, vision models.
GPT-3, AlphaFold 2 using whole data centers. The scale is incredible.
And the results have been impressive, no doubt. But the paper argues we might be hitting diminishing returns.
How so?
Well, the energy costs are massive. And fundamentally, for AGI, these models are still very sample inefficient. They need vast data and struggle with true novelty. Scale might eventually get us there, but as the paper says, eventually is doing a lot of work in that claim.
Right. So just scaling up isn't necessarily the answer. What's the next one? Sync maxing. Sounds like simplicity.
Exactly. Based on Occam's razor, the simplest explanation is often the best. Simp maxing assumes simply models generalize better, make more accurate predictions, intelligence as compression, basically.
Finding the most concise way to represent information. We see this in things like regularization in machine learning.
Yep, techniques like dropout try to prevent models getting overly complex. And minimum description length, MDL, is a principle for selecting hypotheses based on how simply they can be described, plus how well they fit the data.
And the paper connects this to more theoretical ideas. UAI, AISCI.
Right. AIXI is this mathematical formalism of, like, optimal superintelligence. It defines the best agent as the one that finds the simplest models of its environment, using Kolmogorov complexity as the measure of simplicity.
The shortest program to describe something.
Exactly. And Legg-Hutter intelligence, which we touched on earlier, measures how close an agent's model gets to that Kolmogorov simple ideal.
It's a really elegant idea linking simplicity and intelligence.
Yeah.
Practicalities.
Big ones. Kolmogorov complexity itself is generally incomputable. You can't actually calculate the absolute shortest program for most things.
Okay, that's a bit of a problem.
It is. There are approximations, but the paper also raises a deeper, more philosophical critique related to that computational dualism idea again.
How so?
Complexity, the simplicity of a program's form, depends on the language or the Turing machine you're using to interpret it. It's not necessarily an objective property of the function in the real world.
So a simple program might look complex if run on a different kind of computer.
Kind of, yes. However, the paper does acknowledge there is often a correlation. Simpler forms often express weaker, more general constraints, which helps generalization, especially given limited information and selection pressures.
Okay, so simplicity helps, but maybe focusing only on the simplicity of the internal model is too narrow, which brings us to the third one, W-maxing.
W-maxing. Based on something the paper calls Bennett's razor. This one focuses on maximizing the weakness of constraints on the system's function.
Weakness of constraints on function. That sounds abstract. Break that down.
Okay, think back to that computational dualism issue. W-maxing aligns more with enactive cognition, the idea that thinking isn't just internal processing, but arises from the interaction of the whole system, body, brain, environment.
So it's not just about the software's form, but how the whole system works in the world.
Exactly. Pan-computational enactivism, mentioned in the paper, tries to formalize this by looking at the whole agent environment system. W-maxing suggests that generalization comes from having functional constraints that are as unspecific, as weak as possible, while still meeting the goal.
So instead of designing a robot with super detailed instructions for every single joint movement,
You give it a higher level goal and weaker constraints, allowing it to figure out the specifics flexibly, delegating control to lower levels, like biological self-organization.
and this leads to better adaptation.
That's the argument. By weakening functional constraints, you allow for more ways to achieve a goal, making the system more adaptable to different situations. It's not necessarily opposed to simp-maxing. Optimizing for weak functional constraints might result in simpler forms.
Has this been tested?
The paper mentions experiments, yes. On tasks like binary arithmetic, room-maxing approaches showed significantly better generalization than simp-maxing alone. The idea is that delegating control and allowing self-organization leads to better sample and energy efficiency, too.
Interesting.
Examples.
Early stage examples mentioned include things like soft robotics or self-organizing nanoparticles, where control is distributed and emergent rather than rigidly top-down.
And this group-maxing idea, it connects to bigger concepts, too.
Yes, the paper notes it's been used as a framework to think about causal reasoning, language, even consciousness, things that seem to rely heavily on flexible adaptation and context. It considers both form and function within the environment. Wow, okay, that's a really different perspective.
Yeah.
So bringing all this together then, what's the big takeaway from this deep dive based on the paper?
I think the core message is that while scale-maxing approximation, the beginning, has driven a lot of recent progress, its limitations are becoming clearer. The diminishing returns, the energy costs, the sample inefficiency. It suggests the future of AGI probably isn't just bigger versions of today's models.
So we're likely moving towards more integration.
It looks that way. A fusion of approaches, hybrid models, leveraging the strengths of both search and approximation. And these meta approaches, particularly simp-maxing for efficiency and room-maxing for adaptability and generalization, seem likely to play increasingly vital roles.
And we're seeing hints of this already with systems like O3 and alpha geometry, and potentially more comprehensive systems like Ariara, NARS, and Hyperon becoming more significant, especially for building genuinely autonomous agents.
Exactly. It's probably less about finding one single magic bullet algorithm and more about understanding how to combine these different tools and principles effectively, blending brute force scale with elegant simplicity and adaptive functional design.
Right. So maybe a final thought for everyone listening to Mull over. Where will the truly profound leaps in AGI come from? Will it be brute force scaling just getting us there eventually? Or will we be finding deeper, perhaps simpler principles of intelligence? Or maybe, as Dumaxing suggests, learning how to build systems with the most adaptable, least restrictive functional designs. Which path seems most promising for getting to general intelligence?
That's the billion-dollar question, isn't it?